Hi, and welcome to this video where I present the paper Super-Logarithmic Lower Bounds for Dynamic Graph Problems, which was accepted at Fox 2023. And this is a joint work with Huaqing Yu from Princeton University. So I'll try to give in this talk just a gentle overview of what our result is, maybe set the context for the result, and then forward you to the paper if you want to know the technical details. So what we're looking at in this paper is dynamic data structures in particular. And so what are dynamic data structures? Just a quick recap. One example data structure problem you could look at is the prefix sums problem. So in this problem, you could imagine that you want to represent the employees in the company such that you can compute the salary expenses to everyone hired on or before some particular year. And this is basically what we call a query. At the same time, in dynamic data structures, we support updating the data that we're representing. In this case, we would be able to add a new employee, which has a year they were hired and a salary. So one solution to this is that you maybe have a variable for every year you could be hired in, and each of these variables, for instance, the variable corresponding to the year 2005, just stores the total salary expenses to everyone hired in 2005. Right? So it's a simple solution. Initially, you have no employees, so all your variables are 0. And if you then get a sequence of operations like add someone who's hired in 2003 with a salary of 4, then add someone in 2000 with a salary of 2, then query the salary expenses to everyone hired on or before 2004. You could process this sequence of operation, at least with this representation here. When you get the first employee, you just update the total salary expenses in that year by 4. When you get the next employee in 2000, you update the salary expenses by 2. And then when you have to query the total salary expenses, what you could do is just go through all these variables up to 2004 and sum all of them, right? So this gives a data structure whose update time is 1. You just update one variable whenever you get a new employee. The query time, on the other hand, is linear if in the number of different years you could be hired in. So if there are n years, the query time is n. Okay. Of course, you can also solve this problem in other ways, right? You could maybe imagine having a binary tree on top of this sequence of years you could be hired. Every node of the tree stores the total salary expenses of everyone hired in the subtree. And so initially everything is 0. When you add an employee in 2003 to update representation, right, you follow the root to leave path down to 2003 and add 4 to all the nodes. When you then hire someone in 2000, you follow the path down to 2000 and add 2 to everyone on the path. And finally, when you need to query the total salary expenses to everyone hired on or before 2004, you follow this red path down to the year just after, to 2005. And then you can argue that you just have to sum the values stored in these nodes that are hanging off to the left of this path. Okay, so in this one, like the update time is log n plus 1 variables that you have to change, and the query time is log n, basically. So what you see here in these dynamic data structures, they're really a trade-off between the update time and the query time. These are the things that we care about in these data structures. Now, what this worries about is proving lower bounds for dynamic data structures. So these data structures are basically what we care about is the trade-off between query time and update time. And the natural question to ask is, once I have a data structure, can you solve this problem more efficiently? And basically, that's the goal with lower bounds, to show that some achieved trade-off is the best possible, really showing that there cannot possibly exist a better data structure, right? That's the ultimate goal. Okay, so in this work, we prove lower bounds in the so-called self-proof model. And let me just remind you what this is. So in this model, dynamic data structure is a collection of memory cells. Each of these cells stores W bits. We typically think of W as around log n if we have a log n operations. And each of these cells has an address from, say, 1 to 2 to the W, or 0 to 2 to the W minus 1. They have an integer address, each of them. And the contents of these cells are really what encodes the input data. This is where you represent your data. Now, when you want to answer queries in this model here, you're allowed to read up to TQ memory cells. So TQ is the query time. And then you have to produce the answer to the query based on what you saw. And in this model, basically, you can remember everything you've seen in all these cells that you read. And also the cell that you choose to read in each step may depend arbitrarily on everything that you've seen so far while answering the query and the query itself, right? So you can compute any function you like. And similarly, when we have to do updates, we are allowed to read and potentially modify up to TU memory cells. TU is the update time. And along the way, we can remember everything that we saw. And what you choose to do to these cells, how you choose to change the cells may again depend arbitrarily on the update operation you're performing and the contents of everything that you just read while processing the update. So this model was introduced in 1981 by Yao. It's a very clean model in the sense that what we're proving lower bounds on, this TU and TQ, is just the number of memory accesses that your data structure is performing. And then in any reasonable computer, this also gives a lower bound on the number of basic clock cycles that your CPU has to execute. And in this model, right, we assume the computer can do arbitrary instructions, right? You can do everything you choose to do in every step may be an arbitrary function of what you've seen. So basically you have all possible instructions you can imagine. And in this sense, the lower bounds that you prove will apply to any imaginable computational device that you could think of, regardless of programming language and hardware, except perhaps quantum computers, but let's not get into that. Okay, so again, the topic of this talk is improving such lower bounds for dynamic data structures, cell-probe lower bounds. And so let's try to look at just the timeline of what are the best known results in this model. And for simplicity, I'm going to stick to data structure problems with a number of different queries you can ask. This polynomial in the number of update operations that you're performing. So think again of this prefix sum question, right? There's only n different queries you can ask, and there are only n different operations, basically. Or you're only going to look at a sequence of n operations. So polynomial many queries, otherwise the trade-offs are different. The word size here, we're going to assume it's theta log n, also to keep things simple. And then the first data structure lower bounds is due to Fredman and Sachs in 1989, proving basically that the maximum the query time and update time of some data structure problem is log n over log n. Right, so this is the highest lower bound for any data structure problem. So it's not for a particular data structure problem. So this is just for any explicit problem. This is the highest lower bound that had been proved at the time. It took another 15 years before Petrasco and Demain improved this by a log n factor, coming up with a technique that can prove log n lower bounds. And then we had to wait another 8 years before, in work of my own, at Stock 2012, I developed a technique that could prove basically log n over log n squared lower bounds. And maybe one downside with this result here from 2012 is that the technique, for very technical reasons, it can only be applied to data structure problems where the answer to a query has a lot of bits. Right, so at least a log n bit output. Otherwise, there's just no hope of using this technique to prove a lower bound. So in particular, for decision problems where the answer to a query is 1 bit, this log n lower bound by Petrasco and Demain remained the highest at the time. And then another 6 years later, together with Omri Weinstein and also watching you, who's also on this work, we managed to come up with a new technique that could prove basically log n to the 1.5 lower bounds. But these lower bounds also apply to decision type problems where the answer to a query is just a single bit. Okay. Good. Now, if we look at some concrete problems where we prove these lower bounds, let's try to see what they have in common, right? So maybe one problem where we have a super-logarithmic lower bound, so lower bound beyond log n, is this 2D range sum problem. Right? So what you can do here is an update inserts a point in two-dimensional space with a log n bit weight, also integer coordinates if you want to be precise. So you can insert all these points. Those are the update operations. And the query operations are given a rectangle, sum all the weights of points inside this rectangle. So in this case, the answer to this query is 11, 3 plus 8. So this is a data structure problem. How can you maintain such a set of weighted points to support these queries? And this is the data structure problem that my original 2012 paper proved that basically log squared and lower bound for this problem here. Okay. Let's have another look at a data structure problem where we have super-logarithmic lower bounds for. It's basically the same. You insert points. They don't have weights anymore. And the query is also simpler. You don't need to sum the weights of all the points. You just have to compute the parity of the number of points. So there's an even or an odd number of points inside this rectangle. Here, the answer is 0, right? There's an even number of points inside this rectangle. This is a decision problem. The answer to the query is a single bit. And this was one of those problems that we, in 2018, proved a basically log to the 1.5 n lower bound for this data structure problem. Okay. Now, if we, on the other hand, turn to graph data structure problems, right? These are very, very popular. There's a lot of work on graph data structures. There's really been no progress in many years. So, for instance, consider like a classic problem could be dynamic reachability in graphs. So the update operations would be add or remove an edge of a graph. And for such graph problems, no matter what graph problem you look at, the best lower bound that is known is still this log n lower bound by Petrescu and Domain from 2004. Okay, so this data where you can insert an edge, you can insert another edge, you can remove an edge, and then the queries could be, is there a path from A to F in this graph? In this case, the answer is yes. So it's a decision problem. And we have techniques that can prove log to the 1.5 n lower bounds for decision problems, but it has not been done to any graph problem. Of course, the question is there some reason why we have not been able to prove super-logarithmic lower bounds for any graph problems? And I'll try to explain that, yes, there is actually a reason. So to do this, let's look at a notion of a decomposable problem. So the decomposable problem is a natural class of data structure problems. So think of any dynamic data structure problem where you can do a bunch of updates, and then maybe at the end you ask a single query Q. So this is the time axis. You have all these red updates, and then finally a query at the end. So this data structure problem is decomposable if it has the following property. If I tell you what the answer is to this green query on the whole update sequence, and I also have some interval I, so maybe it's something here in the middle. If I tell you the answer on the whole sequence, and I tell you what are the updates outside these intervals, so all the red updates here, but I don't tell you the blue updates, then the problem is decomposable. If I have this answer to the query, I can also figure out what the answer to the query was as if only the blue updates has been performed. So let me try to visualize this. So again, if we look at these search problems with points in 2D, let's say you start by inserting some red points here in before the blue interval. So you insert some points, and then you get to the blue sequence, you insert some blue points. The colors here are just indicating when they were inserted. And then finally, we insert some points after the blue interval. If I look at the answer to this green query here, so it's this rectangle here, and I tell you, well, the answer to this query is 1. The parity of the number of points is odd. If I had performed all the updates, like all the red and blue points here. Let's say I also tell you what are the red points. Right, so I tell you the answer, if everything was there, is 1. I tell you these are the red points. I can look at now the red points in the queries, and I can see, okay, there's the reds contribute 1 to the parity, right? There's an odd number of points here. Now this problem is decomposable because from these two facts, I can compute the answer to the query as if only the blue points have been inserted, right? Because I can basically subtract off the contribution from the red points to the answer. So I can subtract 1 from 1 or add 1 to 1 mod 2, and I'll get that the blue points there must be an even number of blue points inside this region if I know the answer on all the updates and when I know what the red points are. So this is a decomposable problem, but I can see here that indeed there's an even number of blue points inside. So if I have such a decomposable problem, then I can basically go and look at all these previous techniques for proving data structure lower bounds. And all of them are building on this technique of Fredman and Sachs from 1989. So let me try to explain how that one goes and how it relates to decomposable problems. So in their techniques, if you want to prove a lower bound, what you do is you come up with you look at a sequence of updates, you divide them into these so-called epochs. So an epoch has a size of beta to the jth epoch. Basically, the largest epoch is earliest in the sequence of operations, and the smallest epoch is just before the query. And so basically, you think of them, each of these updates as belonging to each of their own epochs. And then to prove a lower bound, what you do is you say, okay, I run my data structures through this whole sequence of operations. Now I'm going to look at how does the memory look when I get to the point where I want to answer the query. These are all the memory cells of the data structure. And what I do is I think of assigning all of these cells to the epochs in which they were last updated. So maybe there's a bunch of cells that are updated in epoch 4, but not during 3, 2, and 1. So I color those black. Then maybe there's some that were updated in epoch 3, maybe also in epoch 4, but they were not updated in 2 and 1, and so on, right? So I color these cells based on when they were last updated. And then this technique of Fredman and Sachs, the main idea is to try and prove that to answer this green query at the end, I have to read or probe a lot of cells from every single one of these epochs. Basically, I have to read maybe a black cell, I have to read a blue cell, a purple cell, and an orange cell. And if I can prove this, then basically I can think of it, I can sum up the number of probes that I need to do in every epoch because these sets of cells are disjoint, and I get a stronger lower bound. That's the main idea in this work. Okay, so what is the reason why you would have to probe a lot of cells from epoch J? Let me try to explain. So let's zoom in on the blue epoch here and try to argue that you have to read a lot from it. So what are the observations? So first of all, you can look at all the epochs that preceded all the big epochs, right? So epochs log beta n down to j+1. All of these epochs happened before the blue epoch, and so they happened in the past. So which means that, okay, this happened in the past, so the data structure wouldn't know what's going to happen in the blue epoch. So the cells that are written here cannot really contain any information about epoch j. Now, if we look at all the future epochs, the ones that come after epoch j, if this beta, the size of which the epochs go down, if this beta is big enough, some polynomial factor in the word size and the update time, then the total number of cells that are assigned to these epochs is very small. Right? In particular, because the update time is TU, and there's only an order beta to the j-1 total updates, they only change TU times beta to the j-1 cells in total. So there's really not very many cells here. And the size of epoch j is beta to the j. So this basically all these cells, there's so few of them that all the bits that are stored in them is not really enough to tell you what is epoch j. Okay, so epoch j is pretty much unknown, even if you look at all the cells here. Right? Basically because epoch j is much, much bigger than the future epochs. So if we try to combine all of this, what we really have the intuitive observation is that everything I do outside epoch j is pretty much independent of epoch j. Right? So they cannot really answer anything about epoch j for me. It's a kind of intuition. So what you then do in these previous lower bound proofs is that you try to hard code or fix everything outside epoch j. Think of it as fixed. And then the only thing that's kind of that you don't know once you've fixed everything outside epoch j, you have maybe a random sequence of updates in epoch j, is that, well, it's only the blue cells, the epoch j cells, that you need in order to answer the query. If you know everything outside, if all these cells are fixed, only the blue cells are necessary to answer the query. And now the answer to the query is the answer as if the whole sequence of operations had been performed. Now, if I have now a decomposable problem, if I have the answer to the whole sequence and I fixed everything outside the blue epoch because it's decomposable, I also know the answer to the query as if only the epoch j updates has been performed. So what this really means is that you can think of the blue cells, the epoch j cells, is pretty much a static data structure for the epoch j updates, right? So it's basically you get the input is the epoch j updates, you store them in a static data structure, one that does not support updates. So you just build a data structure once and for all. And this is basically what these blue cells are. So static data structures, right? The goal here is just you get some input data once and for all, you have to store it so that you can answer queries about the data efficiently. An example problem could be, I give you the road network of a country, that's the data, and then the queries are given two cities. What is the distance between them along the shortest path, right? So here's a city, or here's a road network with some weights on them. And if I ask the query, what's the distance from A to C, you have to output 7 here. That's the length of the shortest path from A to C, right? Here in static data structures, right, they're basically different types of solutions, right? What you could do here is maybe you can pre-compute and store all the answers in a giant table with an entry for every pair of cities. You could also store the graph as it is and then run Dijkstra's shortest path when you get the query. So this gives different trade-offs between query time and space, more space, faster queries, and vice versa. So also for static data structures, we have a bunch of techniques for proving lower bounds. I'm just going to go a little bit quickly over them. So the highest lower bounds in the past, again, if you have polynomially many queries, space of S cells, they basically look like something like log n, right? In 1995, we had like the query time has to be at least log n over log S, was improved by Petrasco and Torok to log n over log of ST over n. Finally, in some work of my own, building on also previous works, we can get up to log n over log S over n, right? So these are basically logarithmic lower bounds. Now, the idea is that if you take these logarithmic lower bounds for static data structures and then apply them to every single epoch using this notion of Fredman and Sachs, basically you can prove that you need to read log n cells from each of these different epochs. Right? You need to read log n blue cells, log n black cells, log n purple cells, and you boost these lower bounds by a log n factor. And this is pretty much what gives these dynamic lower bounds, the Fredman and Sachs lower bounds, and the Petrasco lower bound is basically, Petrasco and domain lower bound is basically take a constant lower bound on every epoch, boosted by a log n factor, This 2012 paper is basically take a log n lower bound, boost it by another log n lower bound. And this last one is something in between. It's a little bit more complicated. But these are the previous lower bounds. Okay. Now, all of these previous techniques, they crucially use that the problem is decomposable. Right? Which basically you can think of it as that the answer to a query should be like a sum over the answers on separate points or updates or something like this. And the question now is, are typical graph problems decomposable, right? So if I have a graph problem like reachability, so I can insert some edges, so insert some edges before an interval I, so insert a bunch of edges, then this interval I comes, there's some blue edges, I don't see what they are, so there's some blue edges here and there. And then finally, there's some updates after the blue interval, maybe I get these edges. And now, if this problem was decomposable, I can say, okay, what is the answer to the query on this full sequence of operations? Can A reach F? In this case, the answer is yes. I also tell you what the red updates are. So all these edges. Can I deduce what the answer to this reachability query would have been if only the blue edges were there? And the problem is, no, you don't know, right? In particular, when you can reach from A to F using only red edges, you have no idea what would happen if only the blue edges were there. Right? Maybe if these were the blue edges, right, the answer would have been no. If these were the blue edges, the answer would have been yes. And there's just no way to deduce this from only the red edges and the answer to the query. So this is not a decomposable problem. And this is the main reason why we have not been able to address these graph problems. They're not decomposable. Right? In fact, like the answer here for such a graph problem is more like an OR of the answer on the red edges and the blue edges. And like either you can reach it using the blue or you can reach it using the red ones. And maybe you need to use a combination. So it's not exactly an OR, but it's closer to like an OR than a sum of answers in particular. So this was the state of the art again with dynamic lower bounds, only for these decomposable problems. And the result of this work is that we find a technique that can prove these log n to the 1.5 lower bounds, also for problems that are not decomposable. Right? And we need a lot of new ideas to handle these OR-type problems. So there's a lot of new novelties in this work. And in particular, we prove this log n to the 1.5 lower bound for a graph problem, in particular dynamic reachability in directed graphs. So you can insert edges, directed edges, and you can ask, can a node S reach a node T? What's shown here is just a figure from the paper. This is basically the hard instance that we end up having. It will consist of a bunch of different graphs, separate graphs, and the answer to the query is basically an OR over these different graphs. Can you reach it using the first graph or the second graph or the third graph? So read the paper for details. But this is the first super-logarithmic lower bound for a graph problem. And I think the nice contribution is it's a new technique that can also handle non-decomposable problems. And I hope that this new technique can be used also to address other dynamic data structure problems that are not decomposable. One natural candidate would be nearest neighbor search. And maybe let me just conclude by saying, okay, there's also a downside to this lower bound that we prove, and that is basically that dynamic reachability in directed graphs is expected to be much harder than log to the 1.5. In particular, the conditional and almost linear lower bounds by reduction from orthogonal vectors. But this is still the highest unconditional lower bound for a dynamic graph problem. So, thank you.